Let us have example for independent increment random processes. In this example, we consider a Poisson point process, and we say that we'll show that the Poisson point process is an independent increment process. So the random process NT, suppose that you have a time or a space, so you have some random points. So let's say this is the instances that a packet is generated by your computer, so some random, or the random times that somebody in Kingston or in another city will call somebody else, and these time instances may be very, very small, or sometimes may be large. So, and time starts from 0, and at time t I define n of t as the number of points in the interval between time 0 and t. So the definition is that n of 0 is 0, so this is initial 1 with probability 1. The second part of the definition of a Poisson point process is n of t is an independent increment process. So this is how we define a Poisson point process. And also, if you consider two time intervals like time t and let's say time s, so here you have n of t and here you have n of s. So the increment here is going to be here. So this is the increment. So this increment is an integer number because this is the number of points in this interval, and it has a Poisson distribution. For instance, the number of cars which cross a section. Or another example, suppose that this is your muscle, okay, and this is your brain, and the nerves transmit some pulses. So the signal transmitted from your brain to your muscle is like a pulse like that. So the position of these pulses is like a Poisson point process. You can approximate the nervous signals as a Poisson point process, and it has a distribution like that. And lambda is the average force, or 1 over lambda is the average force that your brain is asking your muscle to generate. So the number of points at time t0 is 0, at times goes by, so 1 points happen, so n becomes 1, another discrete point happens here, n becomes 2, etc. So you see that the n of t is a discrete state, random process, but continuous time. And at any given time, n of t has a Poisson distribution, because if I put s equals 0, this will become 0. So if I of t comma 0 is equal to n of t. So you have the distribution of n of t, and you have the distribution of any other increments. And these guys, if you consider, let's say, t1, s1, and let's say this is t2, s2, as long as these two intervals, they don't have overlap, I for this interval and this I defined here, they are independent, because we said that they are independent increment process. So this is the definition of Poisson point process. This determines, because if you know n of t, you know how many points are here. If you know this waveform, if this waveform that I'm plotting on, then you know these discrete points. So the information embedded on this set of points also is embedded into NT, and or you can calculate d to dt of n of t, and then you get delta points at these ones. So n of t gives you the discrete points and vice versa. So there's a one-to-one relationship. So as soon as you define n of t, you have defined your Poisson point process and vice versa. So one example for discrete point process, Poisson point process, is that suppose that for any t, we want to calculate the mean of this random process. So what is mean of n of t? Or what is the autocorrelation of this random process? So because this guy has a Poisson distribution, so in this case, lambda t is the parameter of distribution. As you see, as t increases in the previous figure here, so the average, this is the line lambda t. So in average, you expect that you're around this point. Now, we want to find the autocorrelation of n of t. So the autocorrelation is denoted by r, n, t1, and t2. So that means that I have to take a sample of n at time t1 and take another sample at time t2, and then I have to calculate expected value of this one. I cannot easily calculate this one because these two random variables are not independent. However, I could make them either fully dependent or independent. So what I do is that I know nt2, or let's say here I assume that, let's say t2 is bigger than t1. So I write nt2 equal to nt2 minus nt1 and then plus nt1. And this is equal to I of t2 and t1 and then plus n of t1. So if I substitute this one here, I is independent of n of t1 because they are there are two different increments, and the other one, nt1 multiplied by nt1, becomes nt1 to the power of 2, which I know how to do it for a Poisson random variable. So this is how we do it. So I replace this one by this expression. So this guy is independent of this one, and this becomes simple to calculate. So this is what I get. So because this guy is independent of this guy, so this mean is equal to the mean of n of t1 times mean of this guy. So and then plus mean of n of t1 to the power of 2, and this is a Poisson random variable. I know how to calculate it. So mean of this one is equal to lambda t1, mean of this guy is lambda times t1 minus t2, and this guy is the power of this random variable that you can look it up and do it. So once you simplify this, so remember that this was correct when t2 is bigger than t1. If t1 was bigger than t2 was smaller than t1, so then you would have had to change this one. So then you would have got t2 times 1 plus lambda t1. Okay, so in general you can write that this is equal to lambda minimum of t1 and t2 times 1 plus lambda maximum of t1 and t2. Okay, so it's kind of, this is the bigger one and this is the smaller one of the two. So equivalently, you can calculate, if you want to calculate cross covariance of these two, then you have to calculate, because we know that C and N of, let's say, T1 and T2 is equal to R and N of T1 and T2 minus mu N T1 times mu N T2. And this guy is lambda T1 and this guy is lambda T2. Okay, so if you substitute this one, then this term will, the second term will disappear, and this is going to be the cross correlation. So you see that if you put T2 equal to T1, this becomes variance. So the variance also is increasing with time, and expected value is also increasing with time.